This is part 3 in a series of videos in which I'm attempting to explain how to use a logic analyzer. In these videos I'm using an Agilent 1672G, but most of what I'm showing here applies in some way to pretty much any analyzer. You might access the features and the settings in different ways, but fundamentally most logic analyzers, or at least any decent ones, will have these features, and it's just really a case of figuring out where they are on your particular machine. In the first videos in this series I went through how to set up the basics on the analyzer to do the basic configuration, and then how to connect the analyzer to a target board and set the input levels. And in this video we're going to be looking at how to set up a simple trigger sequence. With machines like this, the real power in them is in the trigger mechanism, the way that you can configure the trigger to capture data that you're interested in. To demonstrate this, what I've decided to do is create this small demo board. I don't want to use specific target boards such as Z80s, simply because I'd have to spend time explaining how the processor works, and I want to focus more on the analyzer itself. And once you know how to make all the required settings and configuration, then you can apply that to pretty much any target machine anyway. So what I've got on this board is a ROM, a 16-bit synchronous counter, and a simple clock. The clock's running at about 1.5 megahertz, so it'll give us about a 20 millisecond cycle time for the counter, and that will give us a good cycle time for doing any testing that we want to. I've put some data bytes into the first 8 locations on the ROM, and the target for us in this video is to filter and display just the values in those 8 locations. So firstly, you have to kind of know something about the target you're looking at when you're trying to do any fault finding. So either use a schematic. If you don't have the schematic, then you have to use the analyzer to do a bit of reverse engineering, but that's kind of part of what you'll be using this sort of machine for. Now in this case, the way I've got this configured, I've got the ROM set up so that it is enabled whenever bit 15 of the counter is high. So in other words, it's effectively mapped to address 8000 hex. So the bytes we're interested in are mapped to 8000 up to 8007 hex. So that's what we want to try and filter out from the rest of the data. So I'll start by powering up the analyzer. Again, I'll fast forward you through this bit. And now we'll load our configurations. This is just the same test configuration that I showed previously. Okay, that's now loaded up, so I'll move the camera so you can see the screen more easily. I'm not going to be changing the hardware, it's just going to be left exactly like this. All we're going to be doing here is setting up the analyzer trigger sequence. Okay, so step 1 is we'll go from scratch with the trigger. So we'll select trigger, and I will clear out any existing trigger, so we've got a fresh start, and you'll see the default settings. So select modify trigger, and then we can clear. I want to clear all, and we now have the default trigger for state machine analysis. Now bear in mind that the way the trigger works in timing and state varies slightly, but what I'm trying to do in this video is show how to set up a sequence, and while the steps between timing and state vary somewhat, the overall process of setting up a trigger sequence is the same. First thing we need to do is decide what it is we're trying to capture, and we already know the address. If we just go into waveform and run this, then what you can see is we are capturing pretty much everything. So we're just getting random addresses. So you can see the address at the top and data at the bottom, and mostly the data coming back will be 0 unless we happen to be in the portion of the ROM that contains data. And that's going to be very difficult to try and figure out exactly what's going on. Now, this is going to be a bit contrived just to try to show an example of a trigger sequence. So I'm going to make it more complex than you need to for this example, but just bear in mind what I'm trying to do here is show how to set up the trigger sequence and not show you the most efficient way to set up a trigger. So first, if we go back to trigger, then as I explained in the previous video, what we have at the bottom is a series of terms, and the terms are just really values assigned to a label. You can rename the labels if you want, so we've got A here, or B, or C, or D, you can rename those. I'm going to leave them as they are. I very rarely change them, but sometimes you want to rename them to really help clarify what you're doing. We'll come back to that in a few minutes, but the first thing to do is, you see there are always a minimum of 2 states or 2 steps in a trigger sequence. So in state mode you can have up to 12 steps in a sequence, and in timing mode you can have up to 10 with this particular machine. The number of steps required is obviously going to vary depending on what you're doing. I've very rarely used more than 9 anyway, so there's usually always enough. The first thing we want to do is to insert another step at the beginning, and I'll explain why as we go along. So to insert another step in the sequence, move the highlight to where you, or to the step after where you want to insert the step. So in this case I want to insert a step before the first step we've got here. So I've selected the first one, select, and then up here insert level, and I want to select before. And you've got some macros, some predefined macros here, but the top one is a user-defined step where you set up your own events, so to speak. I very rarely use the built-in macros because they don't really save you much. It's just as easy to define your own, but we'll come back to those in a future video. For now, we'll stick to user-level combination loops. Okay, so we'll select the top one, and then you get this pop-up. So what you have here is a few entries that you need to make. So the first one is where it says while storing. This is, do you want to store data during this step? And a step is a bit like a subroutine in software, or just keep looping around until a certain condition is met. So while this step is looping around, what do we want it to capture in terms of data? And in this case, I don't want to capture any data, so I change this to no state, so I don't want to capture any states. And we now need to decide how this step is going to be exited, what's going to cause this step to move on to the next step. And in this case we want it to find, what it says here, find A, so it wants to find the value of a particular term. So if we just save this and come down to A, doesn't need to be A, it can be any term you want, but we know that the first byte we're interested in is its 8000 hex, so I want to capture the byte before that as well. So I can enter a value in here, and I'm going to enter 7FFF. That is now our term A. You can make these more complex if you want and have as many combinational elements in the term as you require. So it might be we want to use chip enable as well, but I don't need to do that here. I'm going to keep it as simple as possible. So we'll go back up, reselect this step, and so we want to save no states, and we're looking to find term A, or the value for term A. So that will get us started, and once we've found term A, it will cause the analyzer to move on to the next step. So this will keep looping round and round and round until term A becomes true. So in other words, until we find that address that we're looking for. It will do that in this case one time, and then it will move on to the next step. So in this case it will then move on to step 2, which is this one. In this step we want to store any state. In fact, what I'm going to do here is not store any data again. So we're going to come down, change any state to no state, so we're not storing anything. And in this case we're going to look for a different value. And I want to look now for the first byte that we actually want to save. And we know that's at 8000 hex. So I'm going to change term B to 8000. We'll go back up to step 2 and we'll change trigger on to B. So what's going to happen now is this step 2 will loop round and round, and the first time it sees term B, so the first time it sees a value of 8000 hex on the address bus, it will move on to the next step. We'll come back to this else on in a few minutes. So we've now done this, but notice this is, it says here trigger on, and the trigger on it works exactly the same way as the other steps, except that when you hit the trigger, there's only one trigger per sequence. When you hit the trigger, that's what tells the analyzer to effectively start terminating the trigger process. It will then store all the data it's captured in the process, and it will then stop. So though it's always capturing data, it will only bring all that to a halt once it hits the trigger. So you can put the trigger anywhere you want in the sequence. Just bear in mind that once you hit the trigger, you're effectively bringing an end to the process. Well, at least it's the start of the end, so to speak. So now we have found, in theory at least, 7 FFF, jump through to step 2. We've found 8000, and now we'll jump through to the next step, and I want to insert yet another step, so I'll select, and I want to insert the step between 2 and 3, so I select 3, insert level, and I want to insert it before, and again I'm going to use a user level step. In this case I actually want to store data. This is where we're going to start storing our data, and I'm going to store any state, that is any data that comes along we're going to store. And now we need to know how to terminate this loop. So if I save that for now, I'm going to create yet another term. In this case I'm going to set C to 8007. That's the last byte that we're interested in. We'll come back up, and now we can change this to C. So in other words, this step will loop around indefinitely until it finds a value of 8007 on the bus, and then it will move on to the next step. So finally, in fact what we'll do now is we'll actually give this a run. You'll notice it's going to jump from step 3 to step 4, and the arrows show you, these arrows here showing you where the logical progression is through the sequences. What we can do now is try and run this. So if I come back to waveform and we'll run it, and notice it's come through and it's stopped. I'll set the start point to 0. So notice now that rather than capturing everything, it's started to capture at the point where it saw the first step. So where it found A, that's the point at which it started to capture data. But it's going on and it's capturing data indefinitely, and we only wanted to capture those 8 bytes. So these are the bytes, so you can see that the address is correct. It started capturing at 8000, 8001, 2, 3, 4, etc. But we wanted to stop at 7 rather than just carrying on capturing all this data. So we come back to trigger. If we come back to step 4, this is where it's moved on. Once it's found address 8007, it drops through to step 4. And in this case all we have to do is tell it to not store any data, and also to stay in this loop. So notice now that all the steps required, in theory at least, to capture the data that we want are in place. If we now rerun this, you see now it stops capturing data. Got a bit of a loose wire on here, so this is one of the downsides of using breadboards. I'll just try and fix that. Yeah. One thing to bear in mind, if you're messing about with breadboards, then quite often you'll find errors are caused by the breadboards themselves. So notice now that we are capturing data up to 8007, but we've got this byte at the beginning that we don't really want. 7FFF we don't want to capture. Now of course we could get rid of that simply by changing the way that we've got the trigger organized. But I did it like this to show another feature, and that is, although we're only explicitly storing data in step C, where we're storing any state, it would seem to imply that none of the other states should be capturing data because they're all set to no state. But there's another feature in the analyzer that by default it will store what it calls branches. So whenever there's a branch in a sequence, it will store the value that calls the branch. But you can turn that off. If you come across to acquisition control, and then here you've got this option that says branches taken stored. If you set that to off, so now it's saying branches taken not stored. If we go back to waveform and recapture, notice now it's not saving that initial value. So if we come across, we're saving now only the bytes we're interested in. If we go through to the list view, you'll see what the data actually is, and it's the word hello followed by 3 spaces. So we can tidy it up even more. Let's say we don't want the spaces. We'll come back to trigger. In this case, all we have to do is come down here and set the value of the last byte we are interested in, which is 8004. Re-trigger, and now we are saving only the bytes we are explicitly interested in. So very contrived application, but I'm trying here to show how the sequences in the trigger mechanism works. So if we come back to the first one again, just to recap, so no state, it's not going to store anything till it hits term A. When it does that, it drops through to level 2, which is this one, and in this case it's going to loop around doing nothing until it finds term B. When it finds term B, it will drop through to step 3. In step 3 it loops around, and this time it captures data until it finds term C, till it matches term C, and then finally it jumps down to, or drops down to 4, and it doesn't store anything while it's doing this. You can modify this still further and say, if for example, if in step 2 it's looking around for term B, but let's say it finds term C first, then we can tell it to jump straight through to step 4. So this is kind of like an else if in software. So if we now come back out, you can see there's now another arrow alongside the step 2, and basically what it's doing, it's saying this is going to jump directly to 4. You can see another arrow down here if it hits C before it sees B. That's the terms that we're talking about here. So in other words, if it sees address 8004 before it sees 8000, it will jump straight through to 4 and not capture any data at all. So if we go back and rerun it, it's not going to make any difference here because we're counting sequentially, but it's a way for you to control the sequence in a much more complex way. And you can do the same thing with step 3. Let's say again during the capture process you hit the final address prior to when you expect it, then in this case it will jump through to step 4. Again, it will make no difference here because we're counting sequentially, but the point is you can see the logical path with these arrows alongside each of the options. Okay, so that's the basic way you set up a sequence, and every sequence is really the same. So once you understand this progression and how everything interacts and what's in each step, then you can set up sequences that are as complex as you want. You can set up combinational sequences such as this, and we'll look at this in a future video and set up much more complex triggers. Before I finish this video, just a few things that I want to go over that are traps that you need to be aware of. So firstly, we are capturing nice clean data here, and quite often you'll be scratching your head wondering what on earth you're looking at when you capture data. And there can be many reasons why the analyzer will capture things that you're not expecting. Now the first of those, if we go through to format, notice here that I've got the clock, master clock set to only trigger on the rising edge. But if I change that and I capture on both edges, and we go back to waveform and rerun it, notice now that we're capturing, although the addresses are correct, we're getting 2 states per address because we're capturing on the rising and the falling edge. But notice the data values do not match. If we go through to the list view, you'll see that all the values are there, but they're not in the right order, and not only that, but some are incorrect. So if I run it a few times, the values we're getting aren't what you'd expect. Now the reason for that, and it will vary depending on the machine that you're working on. What we're doing here is we're capturing data on the 2 edges of the clock, but the counter, in this case this 16-bit counter that I put together, is being effectively, it's a synchronous counter, but we're capturing data on the analyzer on the same edge that is trying to increment that 16-bit counter. So although the counter is trying to increment all the bits in a synchronous way, on one of the edges it's trying to do that at exactly the same time that the analyzer is trying to capture data. So you've got this race condition between the 16-bit counter on our demo board trying to set all its output bits and the analyzer capturing data. So if the analyzer captures data faster than the counter can update its output, which is quite likely, the analyzer is very fast, and this is even more the case with more modern, faster analyzers, you get much worse looking data because the counter, the target machine, isn't keeping up with the analyzer capturing data. So you need to be very careful when you're setting up the clock and when you're trying to capture data to make sure that you fully understand how the data is going to be updated whenever the clock edges occur. So if we turn it back to rising edge master clock and rerun, we're getting nice clean data and it matches exactly what we're expecting. So just bear that in mind. Worst case of course is if we were to set falling edge. So in this case it's the falling edge of the clock that's trying to update the 16-bit counter, and if we try to capture data on just the falling edge, then we may well end up with a situation where we're capturing just garbage and not the data that we actually want. So it will vary depending on the machine that you're working on, but just bear that in mind. You need to make sure you've got the clock set up correctly. I'll just go back and change the clock back to rising edge. Okay, now the other thing is in the trigger I've shown everything here as being a single capture event, but it might be the case that you know that on the target machine you don't get problems until a certain event has occurred maybe 100 times. So you can do that here, just going to the step where you want it to wait for the number of iterations to reach your target. In this case we'll set this to 100. So in other words, it's going to wait until it hits term A 100 times, and when I start this now you'll see a counter running along the top of the screen, and it will count down each time it hits the A term. So you can see it's counting down, and when it gets down to 0 it will move on to the next step and complete the trigger sequence. Okay, so that's it for this video. Very simple sequence. You can insert new steps, you can change new steps, and in the next video we'll look at some of the inbuilt macros and set up some more complex triggering.